A material has taken away the world by storm with its huge production and assumption to be the world's newest, strongest material in 2013, even more in 2016. This material is known as carbine or also known as linear acetylenic carbon. It is described in the Merriam-Webster dictionary as any of several crystalline forms of carbon in which it is linked in chains containing single and triple bonds. But what really is a carbine? Can it really be considered as the strongest material, even stronger than diamond, and the previously concluded strongest material, graphene? Hi, I am Eliza Arenas, and we will now discuss all about carbine.
Before answering such question, let's first try to see what this carbine is made from. We are all familiar with the element carbon, which has an atomic symbol of C, atomic number 6, and atomic weight of 12.0107 atomic mass units. It has a solid phase at room temperature and is considered as the sixth most abundant element in the universe. This elemental carbon is extremely versatile and has long been used in different fields. Two of its well-known allotropes, or two or more different forms of an element in the same physical state, are graphite and diamond. As we know, some of the widely known uses of graphite is in writing materials, especially in lead of pencils, lubricants or repellents, as refractory material, stabilizer of nuclear reactor, and in making carbon electrodes. Diamond, on the other hand, is widely used in making jewelry, drilling, grinding, or cutting materials, as facial exfoliator, and in audio equipment. With the recent advancement in science and technology, different attempts were also made into making synthetic allotropes of carbon, such as fullerenes in 1985, carbon nanotubes in 1991, and graphene in 2004. Although this may have long been discovered already, it was in these years that they were widely known. The most convenient and correct classification scheme for carbon materials is their division according to the type of chemical bonds, such as according to the type of hybridization of the valence orbitals. The three-dimensional or spatial polymer of carbon, diamond, corresponds to the first state sp3. The two-dimensional or planar polymer of carbon, which is graphite, corresponds to the second one, or sp2. Going a little back to its history, the first attempt to synthesize chain-like carbon was made by Adolf von Baeyer back in 1885. However, in the framework of the stepwise synthetic procedure employed by Baeyer, he did not succeed in isolating of even tetraacetylene, which is an antibiotic, and is extremely unstable. The instability of the lower polynes led Bayer to develop a strain theory in which he postulated the impossibility of preparing chain-like carbon. Now let's dwell on another developed allotrope, which is carbine. It is the only form of carbon that has not been synthesized, even though researchers have been studying its properties for over 50 years. However, in 1959 to 1960, systematic investigations of the oxidative coupling of bis-ethinyl compounds were performed at the A.N. Nesmyanov Institute of Organoelement Compounds of the USSR Academy of Sciences. This version of the oxidative coupling reaction was named oxidative dehydropolycondensation. Research in this area led to the discovery of a linear form of carbon, which is carbene. Now there are different methods for obtaining carbene, such as this oxidative dehydropolycondensation of acetylene, which led to its discovery. We also have polycondensation of carbon suboxide with bis bromomagnesium acetylate, the hydrohalogenation of polymers, the hydrogenation of polyacetylene, synthesis of carbon in a plasma, laser-induced sublimation of carbon, deposition of carbon from an electric arc, ion-assisted condensation of carbide, and others. But we won't dwell much on those and focus on what carbine can really do. Regarding its structure, as mentioned before, carbine is a chain of carbon atoms held together by either double or alternating single and triple atomic bonds. That makes it a true one-dimensional material, unlike atom-thin sheets of graphene that have a top and bottom or hollow nanotubes that have an inside and outside. Now going to its properties. Carbine's mechanical properties are theorized to excel all known materials. In a paper of Boris Jakobson and colleagues from Rice University in Houston, showed that carbine's tensile strength, or the ability to withstand stretching, surpasses that of any other known material and is double that of graphene, the flat sheet of carbon atoms that is often held up as a supermaterial. They also calculated that carbine has twice the tensile stiffness of graphene and carbon nanotubes, and nearly three times that of diamond. Stretching carbine as little as 10% alters its electronic band gap significantly. The material is stable at room temperature, largely resisting crosslinks with nearby chains. Carbine, especially in the crystalline state, exhibits a remarkable inertness toward various oxidizing agents. Only the reaction of ozone with carbine results in its completion degradation. It displays a high chemical inertness approaching that of diamond. In terms of electrophysical properties, it displays photoconductivity on irradiation by a light source. The investigations of thermodynamic properties have shown that the heat capacity of carbine exceeds that of graphite at 80 Kelvin with a factor of 1.5. According to their heat capacity, the allotropic forms of carbon form the following series: diamond less than graphite and less than carbine. The existence of carbine opens up prospects for the creation of unique materials on its basis. Carbine is a high temperature phase of carbon, which is stable at a temperature greater than 2000 degrees Celsius. It is distinguished from other carbon materials by its stability with respect to the formation of compounds with hydrogen. This makes carbine very promising for application as the material for the devices for controlled nuclear fusion. Carbine is a semiconducting carbon and is thus the missing linkage in the series of carbon materials. Diamond is an insulator and graphite is a conductor. Coupled with the possibilities of the ion beam technology for preparing carbon films with specified properties, it opens up prospects for creation for a new element basis for microelectronics based on carbon only. An important feature of carbon is its ability to be transformed into diamond under high pressure and high temperature conditions. In contrast to graphite, the transformation of carbide into diamond does not require the introduction of catalysts and thus allows the preparation of a pure diamond material. The discovery of carbon in carbon fibers, prepared by the pyrolysis of polymers, opens up prospects for the creation of ultra-strong carbon threads inasmuch as the defectless filamentous crystals of carbon should be theoretically the strongest of all known materials. Finally, carbon has revealed a number of properties which are very valuable for application in medicine. This includes such properties as non-toxicity and high biocompatibility, as well as considerably greater thromboresistance as compared to other materials. Carbine-containing polymer materials for medical purpose are promising for application in reconstructive surgery, urology, and stomatology. Carbine is one of the most promising materials which are still being studied by scientists and engineers in order to further improve the existing materials and to make the world a comfortable and more comfortable place to live in. Thank you for listening.